in the next example. So let's just say they give you a person with this mass and this density. They want you to find the volume, right? The volume of the person. So we rearrange this. Volume is mass over density. So the mass is 81.5 and the density is 985. And kilograms per meter cube. So you're gonna get a volume on meter cube. So if you do the division, you get 0.0827 meter cube. Just how you can use the equation of density, how you can rearrange it, all right? And then let's calculate the pressure on an area of this. So in this case, we just use the definition of pressure, which is force divided by area. Now, the pressure is due to the weight of the person. So the pressure here will be the weight, that's the force, divided by the area. That's the area. The weight is 81.5 times 9.8. That's divided by the area, 4.50 times 10 to the negative 2. Meter square, Newton per meter square. That's Pascal. So if you do the division, you get 1.77 times 10 to the 4 pascals. Remember, Newton per meter square is Pascal. All right? So simple, just so you see how you can use these two equations. And then we have the other definition of pressure, which we use a lot in chemistry, right? You have a tube in this shape with mercury inside, and you're gonna learn today why we use mercury a lot in experiments, right? In thermometers, for example. But basically, you have a column difference of 0.115 meters, right? A difference on height. That's open, and this is closed. But the problem is asking you to find the gauge temperature, the gauge pressure in here, not the absolute pressure, just the gauge. So this is found by using the other definition of pressure, density of the liquid or fluid, gravity times height. The density is the density of mercury, which is this, very high, times gravity times height. And that's the gauge pressure. If you calculate that, you get 1.53 times 10 to the 4 pascals, because kilogram per meter cube times meter per second square times meter, that's Newton per meter square. All right? Everything is in metric system, so you know that will give you pascals. Now, that's the gauge pressure. If they were asking you for the absolute pressure or the total pressure, that will be the gauge pressure plus the atmospheric pressure. And you know from yesterday, the atmospheric pressure is 1.013 times 10 to the 5 pascals. That's the That's what you have to add to this to find the total pressure. All right? So just for curiosity, let's see what we will get. Right? So one and 1,300. So 116, 600 pascals, about 1.16 or 1.17 times 10 to the 5 pascals. All right. So there you have it. Okay, that's pressure density. Okay. So now that when we introduce this, then we started doing an example on buoyancy, right? We talk about a helium balloon. Let's look at this experiment. So one experiment that we can do to check buoyancy is by having a spring scale. With a hook here. And you have a beaker all right? And carefully, we have the beaker with water, so this is a H2O. And we have here a mass, which is hanging there inside the water. And on top of this, or at the bottom, there is another scale. So here I place another scale. Right, this is scale, and this is a spring scale as well. Like the hook that you guys use in the lab. Some of you remember? So that's also scale. You want to have two different readings because that's, oh, sorry, that's oil, not water. This is oil. And what's the data they give you? I mean, in an experiment, right? You will know a few values. You will know the mass of the beaker. So let's put it here. The mass of this beaker is 1 kilogram. The amount of oil, so the mass of oil is 2 kilograms. I mean, you can measure that. You've done that in the lab. I mean, you guys know how to do that. And the block is made of iron. It's an iron block. So the mass of iron is also 2 kilograms. And the density of oil is 916 kilogram per meter cube. Okay. So given all the information that makes sense, you know, you are being asked to find the reading on both scales. That's a typical example to show buoyancy, okay? Because the scale acts like a rope. There's tension in there. So you basically want to know the tension on the scale here. And then this scale is reading all the force exerted downwards. So let's start with the top scale. Let's analyze the top scale. So this is iron. And on the top scale, like I said, there is tension. That's the reading. And what else is acting on the iron? Obviously, its weight. The weight of iron, but is immersed in oil. So, buoyancy due to oil. The object is in equilibrium. So, the weight of iron, that has to be equal to the buoyancy plus the tension, which is the reading on the scale. So I just have to subtract the weight of iron minus the buoyancy. And here's the question for buoyancy. Okay. So that's iron. So I need a density of iron. So you can go in the slides or you can just go and type density of iron. And if I type it, I get 7,870. All right. So the density of iron is 7,870 kilogram per meter cube. All right. So let's calculate this. Let's find the reading on the scale. Okay. So the weight of iron, it says that the weight of the object, density of the object. Oh wait, but I have the mass of iron, so I don't need that. I can just use 2 times gravity. That's the weight of iron. That's equal to the buoyancy. That's what I need. So the buoyancy is density of the fluid, gravity. I do need the volume of iron. The volume of iron, remember, density is mass over volume. That's why I did a problem before. So volume is mass over density. Mass over density. So mass over density. That. Plus tension. So my tension is 2 times 9.8, that's 19.6 minus, so let's do that. Well, I have it here, and let's double check. 916 times 9.8 times 2 divided 7,870. Yeah, 2.28. So if we round it, we get 17.3 newtons. That's the reading on the top scale. So not 19.6. Because of the buoyancy, makes sense. That's the apparent weight, by the way. I think I mentioned that yesterday. The reason why bodies seem to be less massive in fluids, in water or oil, is because of the buoyancy. So that makes sense. What about the bottom scale? Bottom scale. All right, guys. So let's do it here. Obviously, the weight of the beaker, the weight of the oil, right? The weight of the oil, the weight of the beaker. So weight of the oil plus weight of the beaker. But guys, here's what you have to remember, right? That buoyancy is acting on the mass, on the iron. And you know that forces come in pairs. For every action, there is an equal and opposite reaction. Because the fluid is not a solid, but it's still, right? It's still inside the oil. So the buoyancy that acts on the iron is identical to the buoyancy downwards that acts on the scale. That's the extra force acting on the scale. So we just have to add the buoyancy. The weight of oil, the weight of the beaker, plus the buoyancy due to the oil, which we found it here, 2.28. Right? That's the rate. Remember, the buoyancy is equal to the weight of the displaced fluid. That's what you have to add in order to get all the weight on the bottom scale. So the weight of the oil is 2 times 9.8. The weight of the beaker, 1 times 9.8. And the buoyancy, 2.28. So this is 19.6 plus 9.8 plus 2.28. About 31.7 newtons. All right. That is a nice experiment where you can find the effect of buoyancy using scales, bottom and top. Okay? Guys, I need you to ask questions, please, because I know this is new. So, are there any questions about this?
All good.
You know why? Because when I was a student, this topic was a bit, there's a few new things in here, right? We're talking about densities, buoyancy, so you need to digest some of this. Unfortunately, on summer, we have to rush a little bit. I'm trying to go as slowly as possible, but yeah. Okay, so I'm gonna believe that you guys are understanding this. We did already 2 examples. I'm gonna do a couple more. Let's do the apparent weight. All right. Okay, so I want to leave that in there. The apparent weight is a typical example. So normally, another way to test buoyancy or to calculate densities of unknown objects is to give you a sample of an unknown material. Like, let's just start. So if you're doing a physics or chemistry lab, they can give you an object. You don't know what this is, but they tell you that, or you have a scale, so you know that it's weight. So you're given an object. You don't know what it is, but you know that the weight of the object is 300 newtons. I measure it here in the middle. In water, the weight of the object is now 200 newtons. Oh, sorry, in alcohol. In alcohol. It's good. Let's use other fluids. The only thing you know is that the density of alcohol is 700 kilograms per meter cube. So they want you to find the volume and the density of the material. You see, that's the Eureka Archimedes principle, right? He was given a crown, and they wanted to find if it was made of gold, and he found that there was some displaced water in his bathtub, and then using that, he calculated the buoyancy. With the buoyancy, you get the volume of the object, mass over volume, you get the density, and then you can kind of, compare what's the density of gold. Well, in this case, let's see what this is. All right? So, why is the weight of the object less in alcohol? Because of the buoyancy. So you can write 200 is 300 minus the buoyancy. That's it. So obviously, the buoyancy due to alcohol is 100 newtons. And we know the buoyancy is this. And I know the density of alcohol. That's what you do it with water, right? Water is 1,000. Alcohol, you probably have to be more specific, but you have it. So 100 is the density of alcohol times gravity times the volume of the object, because it's all in water. So you can just use the volume of the density of the volume of the object. The density of, so 100 is 700 times 9.8 times the volume of the object. So the volume of the object can be calculated very easily. About 1.46 times 10 to the negative 2 meter cube. That's because everything is in newtons, kilograms per meter cube, so that's meter cube. Easy, right? And then, what's the density of the object? That's the mass of the object over the volume of the object. Well, I have the weight of the object. So if I have the weight of the object, the mass of the object is 300 over 9.8, that's the mass, divided by the volume, which is this. And I get a density of 2,100 kilogram per meter cube. So then you can go and take a look what type of material it is. That's a good experiment. These two are good experiments. The only issue is that you will have to find like different fluids and all that. We could develop it, but yeah, you know, you have apparent weight and you have scale readings. Both you see applications of buoyancy, the Archimedes principle. All right. All right. Let's do one like it's in the assignment. So in the last problem on the assignment, they give you a hook spring, and then you attach a balloon and it's gonna go up. You know why the balloon goes up now. So you wanna find the extension of the spring. So that one is for you guys to do. I'm gonna do a similar one here. So, and with this, you can do the one in the assignment. And by the way, there's a problem like this in the assignment, there's a problem like that. So I'm doing problem, and there's a problem like the one I did with pressure. So you have seen a good amount of variations. The balloon problem is also in the assignment, the one that we did yesterday. Okay. Let's do an application of the Archimedes principle. So then we can start talking about fluids in motion. All right. Okay, so I can erase this now. Let's do that in there. So in here, they give you a situation like this. You have a container all filled with water, and at the bottom here, there is a spring with some constant K. And then you are given same container, right? But then you are gonna attach maybe wood, right? So now the spring, so now you have a mass who is going up. So this is the spring now. You see, it has been elongated, stretch, some value X or delta L, same spring and mass. Okay, so they give you the spring constant K is 160 newtons per meter. The container has water, that's H2O. And yes, of course, this mass is wood. Yeah, wood wants to go up, right? With density of wood, 650 kilogram per meter cube. All right. And the mass is of 5 kilograms. Do you need that? Yeah, you got the volume. All right, so you have the mass of wood, the density, and you want to know how much the spring was stretched due to that piece of wood. Guys, it's the same that we did with the scale, but now it's inside the water. It's all about drawing the forces acting on that. Okay? So it's in equilibrium, right? That mass right now is in equilibrium. So you just want to draw the forces acting there. The mass, there is still gravity always. So mg you're gonna see this tomorrow, but if you attach a mass to a spring, the spring wants to bring it back. So there is a restoring force. Hooke's law. That's Kx. Kx. Downwards one. So what's making the mass go up? The buoyancy. There you are. So my equation of equilibrium is buoyancy equals to the weight of the wood plus the force on the spring. Very easy. Very easy. So it's all about drawing forces. What we did before, right? You think about it. We're still applying Newton's laws, forces, equilibrium. We're just now adding the whole idea of fluids. Buoyancy is what? Density of the fluid times gravity, times the volume immersed. The whole wood is immersed, so the volume of the object. Okay. The mg is just 5 times gravity. And kx is 160x. So this part of the equation is this. Gravity, we know it. Density of the fluid, density of water is 1,000 kilogram per meter cube. That you should memorize. That's everybody should know that. The volume of the object. If I have the density, I can find the volume. Again, that's why I did the first problem today, right? Volume is mass over density. So this will be 1,000 times 9.8 times 5 over 650. Okay. 49 plus 160x. All right, so let's find this number. Subtract 49, divide by 160. So it takes more time to draw it than to solve it, right? So 1,000 times 9.8 times 5 over 650. So I get 75.4 there. So 75.4 equals to 49 plus 160x. If I subtract 49, that's 26.4 equals to 160x. So x equals to that divided by that. 0.165, 0.17 meters. Or 17 centimeters. It makes sense. It's about like a ruler. So there you have it. There you have it. Okay, you've seen quite a few applications of the Archimedes principle. It's mostly what you have in assignment 9, chapter 9. But now we have to talk about fluids in motion. Are there any questions? So like I said, there's a problem in assignment 9, which is very similar to that. So now you know how to solve it. Okay. Okay. So we're going to finish chapter 9 by talking about fluids in motion. I will show you the slides and then we'll do a few applications. There are quite a few applications of fluids in motion, but we're going to focus on some specific ones that you will see in real life. And then that will be that will be the end of this chapter. All right. Yeah, you can find densities like that. It's very, very easy. So remember, I said that air can be considered to be a fluid. In fact, we're going to do a problem today of aeronautics, like a plane and the fluid and pressure difference in a wing, right? You probably have heard that the reason planes, right, the reason the wings are shaped the way they are is because of the fluid of air and the pressure difference on the top and the bottom of the wing. The same can be said about cars, right? That are moving in this fluid, in air. And that pressure difference, it's due to, well, of course, the forces acting on top and the bottom, but also they are the ones responsible to the way they glide or they fly. If you have ever done hang gliding or paragliding, which you should, I recommend it 100%, you can feel the air making you glide, right? It has to be on a sort of windy day to have actually a good effect and stay on the air quite some time. But the principle behind that is the pressure difference and the difference in the speed on the top and the bottom of the wing. And that is because of fluids in motion. So we can assume in most cases that a fluid can be non-viscous, so there's no viscosity. Incompressible, so it has a laminar type of fluid, is steady, so it has a speed and a flow rate. And it doesn't have any turbulence. All right. If we assume that, then we can assume two important things. When a fluid, water in a pipe, for example, is moving, we can assume that the mass of water is constant and that the energy transfer from one point to another is also constant. But remember, if you have a pipe, it can be at two different levels. That means there will be a difference on pressure. So the pressure at one end won't be the same at the other end. But that's okay, because the difference on pressures give you a difference on the flow rate. But also, if you have ever looked closely at pipes, there is a difference in the cross-sectional area. Easy. Some of you are probably watering your plants right now in summer, right? So if you're watering your plants, you probably place a device in your hose to make the water travel faster, longer distances. By placing a device in your hose, you are reducing the cross-sectional area. By reducing the cross-sectional area, you increase the flow speed of the water coming out of the hose. That's because of mass, conservation of mass, which we call it the equation of continuity. So there it is, right? You have a pipe with different cross-sectional areas, A1 and A2, and the mass of water on both ends has to be the same. So you have the equation of continuity here. The area 1 times the speed here is equal to area 2 times the speed here. And guys, remember, right? Mass depends on what? Density and volume. Well, here it is. Density and volume. Density and volume. But the density is the same, so it cancels. And in the case of the volume, we assume delta X to be the same for both. So you just stay with area, right? So V1 times area 1, density cancels, equals to V2 times area 2. Okay? By the way, area times velocity has a name. We call it the flow rate. The flow rate of water in a pipe is equal to the area of the pipe times the speed of the fluid. The units of flow rate, obviously, if you think about it, right? If the area is, by the way, there's a symbol for flow rate. Yeah. Q. We're going to use it again today for something else, but flow rate, this is a symbol for that because it's also called caudal. All right. That's area times velocity. So meter squared times liters per second, the units are meter cube per second. These are the units for flow rate. So sometimes that's what they give you. In real life, they give you the flow rates on pipes. They don't give you the speed and the area, right? They give you the flow rate, and with that you can figure it out the area or the speed of the fluid. Okay, so to understand the motion of a fluid in pipes or in situations like this, right? We also can use the conservation of energy. Again, we are assuming no viscosity, laminar type of flow for the liquid, right? So it goes steady without any turbulence. So the change on kinetic energy and the change on potential energy is equal to the work done by the forces. But there are two forces. There is pressure here and pressure here. And remember, pressure, right? So P1A1 is the force here, P2A2 is the force here. So the difference between the forces, right, times the volume, that will give you the work. Work is also defined as pressure times volume, by the way. That's an equation we're going to do later on. There's a proof here. So Fx and F is P1A1, but area times distance is volume. So there you have it, okay? You don't have to believe it. That's a proof that work is also pressure times volume. So pressure here is different than pressure here. So this is the work done between the two pressures. That's equal to the change on kinetic plus the change on potential. So you can factorize m's, and volume is mass over density. So you can cancel our mass. You can multiply by density, and then look what you get. You get P1 minus P2 is equal to 1/2 density V squared minus 1/2 density V1 squared plus rho G Y2 minus rho G V Y1. So I can, well, you can rearrange this equation by this. Look at this equation here. There you are. P1, 1/2 rho V1 squared plus rho G Y1 equals to P2 plus 1/2 rho V2 squared plus rho G Y2. This is constant. That's the Bernoulli principle or Bernoulli equation. That's the equation for fluids. And by the way, there's a relationship between V1 and V2, right? What is it? Well, A1 V1 equals to A2 V2. That's the continuity equation. So you can use both the continuity equation and the Bernoulli equation, study the flow of fluids in pipes or in different situations. I can use that to understand pressure difference between the top and the bottom of the wing of an airplane, right? And by the way, if I have that, right, let's use this. Well, then I'm gonna erase the board, but let's see what all the consequences of that equation. You see, that equation in physics, in aerodynamics, is very important. Okay. So that's the equation we have, right? So depending on the type of situation, if you're going from the bottom to the top, you expect the one on the bottom to have more pressure than the one on the top. So P1 minus P2 is your delta pressure. We call this pressure difference. And my pressure difference, right, if I reaccommodate this, is 1/2 rho V2 squared minus, this goes to the other side, 1/2 rho V1 squared. This is the, think about it, right? This is the kinetic energy of the fluid. And the other one is the potential energy of the fluid, rho G parenthesis Y2 minus Y1. Right? This is the potential energy due to the different heights. That's why you have Y2, Y1. This, if you know the pressure difference and you know the height difference between the top and the bottom, you can know the difference in the velocities between the top and the bottom. This is the velocity on the top, on the bottom, right? Yeah. So on the top will be more than the bottom. So what does this tell you? You have more pressure at the bottom, but you have less velocity at the bottom. That's another consequence of the Bernoulli principle. The more pressure, the less the velocity of the fluid. That's because of this, right? But as you decrease the pressure, you make it up by increasing the velocity. You see, one thing, if you guys travel, like I do, right, a lot, like over countries, one issue that we encounter, especially if you go to certain countries, right, is pressure difference issues. If you go to a building here in the US and you want to take a shower, you're normally going to expect that the shower has a flow rate okay enough, right? Even if you're in the top floor, you can still take a shower. In other countries, it's not like that. In other countries, especially overpopulated, because of the amount of buildings or houses, the pressure difference is not enough to compensate for this. So you're in a situation where if you're in the top floor and the building is too old and the water tank doesn't have enough power, it doesn't have enough energy to give to the water, so the water flow is going to be really weak. How do you compensate for that? One idea is to place a tank on the top of the building. And you guys have seen that probably, right? Some buildings have tanks at the top. So then they can make up for the, for the high difference from the bottom and from the top. Right? It's easy for water to flow downwards than upwards because of this pressure difference. Okay? So a lot of consequences of this, right? And like I was saying, right? If you combine the continuity equation, then we can solve quite some applications. That's what we're gonna do now. All right. Let's start with a typical example of a water tank with a hole. You probably have seen it, right? There's a water tank and there's a hole, and then you see water flowing outside. Why? And how do you know? Why does it flow like that? I mean, it makes sense, but can we physically compute the behavior of water? Yes, we can. So you have a large water tank. Which is 3 meters high. And is filled with water to the top. That's water there. And then there is a hole here at the bottom. Uh, 0.800. So it's not really at the bottom, it's a bit on the top there. So the hole is around here. 0.8 meters here. Okay. So how fast is water? Is water flowing? Remember, guys, there's no motion here, right? The water is still. There is where the water is flowing. All right. So both this and this are open to the air. All right. So P1 and P2 are the same. There's no pressure difference because they both are at the atmospheric pressure. All right. However, there is a pressure difference due to this difference of height. And the water is not moving here. So let's call this V2 and V1 here, 0 meters per second. And the difference of heights is 3 minus 0.8 to 0.2 meters. So this is 0. So I have Y1 is 2.2, and if I make this my reference, Y2 is 0. So the only factor on the top is rho G Y1. Because that's 0 and the pressures are the same, P1 and P2. So rho G Y1 will be rho g y1 minus y2. y1 minus y2 is 2.2. Right? The y1 minus y2 is the difference between the levels of water. And the only factor there now will be, but that's the same as that, will be this, the kinetic energy of the fluid. So, guys, potential equals to kinetic energy. Is the same, but now with fluids. So we have to use density instead of mass, if you think about it. It's just that, right? Potential energy, now we use density, equals to kinetic energy. So we didn't even need to know the density. Density cancels. So V2 is just the square root of 2 times 9.8 times 2.2, basically the square root of 2gh. You get 6.57 meters per second. All right? So that's a classic example of the Bernoulli principle. Very simple one, because you don't have to worry about the velocity here, just here. They both are open to the air, so the pressure difference is going to be 0. The only pressure difference is due to the potential, so that's what we see, rho gh, if you think about it, right? That's equal to the kinetic energy due to the flow rate here. All right? That's a simple example, though. Let's do one more interesting one where you don't have a high difference, but you have a cross-sectional difference, like an area difference. Okay? Any questions, by the way, about this? You know what you can add? I remember this because this was my midterm years ago. Oof. You see how you have that? Which is that? What's this? Right? You remember? I remember I was asked, easy though. How far does the water reach after leaving the tank? Try to do it. I know what I'm doing. You have the height, and it's moving like that. And you have, of course, this. So you can find that. You can find the time and the range of water. Okay? So there you are. That's an extra for you guys. Let's do another example. This one, they give you a liquid that is flowing horizontally through a pipe. So first you have a larger cross-sectional area, and as it flows, it goes to a smaller cross-sectional area. All right. So this liquid has density 1.65 grams per centimeter cube. All right. The areas. This area is of 10 centimeters square, and this area is of 2.5 centimeters square. And the flow speed here So as it goes like that, V1 is 275 centimeters per second with a pressure P1 of 1.20 times 10 to the 5 pascals. You're gonna calculate the pressure here, and of course, the velocity here in the smaller area section. All right. So you have to use both the Bernoulli equation and the continuity equation. I'll let you guys think about it for a bit. Let's do the velocity. That's the easy one. Area 1, V1. Area 2, V2. Okay? In problems like this, it's very easy to find the second velocity. And don't worry about the units so far, because look, area 1, velocity 1 equals to area 2, velocity 2. So 10 over 2.5 is 4. 4 times 275 is 1100 centimeters per second. Do I want to leave it like that? Maybe not. So 11 meters per second is my V2. Easy. That's how you find the second velocity. All right? So now I need to find pressure. And this is an easy problem because it's horizontal, so they are at the same level. If they are at the same level, my Y2, Y1s, they cancel, they are 0. There's no Y1, Y2 difference. It's only P1, V1, P2, V2. So, I have space here. Yeah. So to find P2 using the Bernoulli equation, P1 plus 1/2 rho V1 squared equals to P2 plus 1/2 rho V2 squared. P1, P2, I want P2, V1, 2.75, I divide by 100, right? Meters per second. V2, I have it, and rho. That's this, but hey, grams per centimeter cube. I told you yesterday, you are gonna be given, in some cases, densities like this. In fact, this is the most common way to find densities in the bibliography, in grams per centimeter cube. That's what they use in chemistry a lot. Well, grams per centimeter cube, to go to kilogram per meter cube, you just multiply by 1,000. So this is equal to, by 1,000, 1,650 kilogram per meter cube. Nice, right? So I have the density. So I put it in here. So P1 is that. Plus 1/2 of 1,650 times V1, 2.75 squared. That's equal to P2, which is what I want, plus 1/2 of 1,650 times 11 squared. All right? So here, this number will give me 120,000 plus this number is 6,240. That's equal to P2 plus this number is 99,825. So this plus this minus that. If you do that, P2 is 26,415 pascals. Quite a lot, right? Well, divide by no, it's about 0.27 atmospheres. 0.25, 0.26, 0.25 atmospheres. So it's still less than the atmospheric pressure, but so that's another example there. Questions? You've seen two now. One with a high difference, one horizontal case with a continuity equation. Any questions? Come on, guys.
My quick question, can you repeat why we didn't use the half part of the other equation? What would a y1 be? Like if it was a
They're
different
at
type
the
of
same
problem?
level, right? Since they're at the same level,
Mm-hmm.
y1 minus y2 is 0.
Okay.
That's why. So if you were to subtract this from here, right? y2 minus 1y is 0. So this can be
I
1.
got you.
That's 1. So
Okay. Thank you.
again, this is a new concept. I know that it's like conservation of energy if you think about it, but I would highly suggest that you guys practice this, review it. There are problems in the assignment and in Cengage. I'll do a couple more. I have one. Let's do the aerodynamic situation, the airplane. Okay? All right. An airplane or a jet airplane flying has a mass of, so the jet airplane in level flight has a mass of 8.66 times 10 to the 4 kilograms. And the two wings have an area, so the two wings have an area of 90 meters square. You are going to find the pressure difference first between the top and the bottom of the wings. All right. So if you think about it, right? So you have the wings, right? The mass of the airplane goes down, or the weight, and you have the area of the two wings. So you can estimate a pressure difference between the top and the bottom. The wings have some thickness, obviously, right? So, A, what is the pressure difference on the wings? Your delta P is the weight divided by the area. It's just that. It's just that. Okay? So it's 8.66 times 10 to the 4 divided by 90 newtons per meter square. So that's good. So it's going to be huge. It's going to be about 9,430 Newton per meter square. And let me point out P2, P1. So P2 minus P1 is this. Why am I doing that? Because of part B. If the speed of the air under the wing, so if the speed of the air, right, let's put it like this. Here, the speed here is 225 meters per second.
Wait, I have a quick question. For
Yeah.
the equation up there, you put weight, but you put just the mass value. Is this supposed to be weight or is it supposed to
Oh,
be just
yeah,
the mass
sorry.
value?
Yeah, that's I put it. Yeah, yeah. mg over, yeah. It still give it that value. Just double check. I'm pretty sure I did it. Yeah. Okay, so if the speed of air at the bottom is that, you want to find the speed of air on the top. They don't tell you, but with the pressure difference, you can ignore the thickness already of the wings. And because of that large value and this value of the speed, it makes sense to ignore the level y1s and y2s. So you remember, P plus 1/2 rho v squared plus rho gy, that's constant. So if I ignore that level, the y difference, right? So I have this. I can write this. P1 plus 1/2 rho v1 squared equals to P2 plus 1/2 rho v2 squared. And I have P2 minus P1. I can do this minus this by moving this there, and V1, and I know V2. So I can write the equation like this. 1/2 rho V1 squared minus 1/2 rho V2 squared equals to P2 minus P1. But P2 minus P1 is this. There you go. And what's rho? Rho is air, right? This is air. The density of air from the table that you guys have in the slides is 1.29 kilogram per meter cube. So air acts like a fluid. All right, so I have rho, I have V2, I can compute the value of V1. All right, let's do it here. So one half 1.29 times V1 squared minus 1/2 1.29 times 225 squared, that's all equal to 9,400. This number, if I compute that number, I get 32,653. So 1/2 minus 32,653 equals to 9,400. So 1/2 1.29 V1 squared equals to, let's do that, 32,653 plus 9,430. That's equal to 42,083. Multiply by 2, divide by 1.9. So V1 is the square root of 2 times 42,083 divided by 1.29. If you guys do that, it gives you about 255 meters per second. So there is a 30 meter per second difference between the flow of air on the top and the bottom. That's what levels up the flight. All right. Now, what happens if you start increasing the altitude? Guys, what happens, and you should know this, is that the more altitude you go, the lower the density of air. That's why it's harder to breathe when you're climbing a mountain. If you lower the density of air, the pressure difference, right, is way smaller. Your pressure difference is smaller because if you have lower densities, you have a lower pressure difference, then you can no longer support the aircraft. If you don't have enough pressure difference, you don't have enough velocity difference. A good pressure difference gives you a good difference on these velocities to make the flight stable. That's why the altitude of the plane is not random. It is at an altitude, so this actually can actually happen, right? Okay. So I'll see if we can do at least one more later on. This is basically chapter 9, guys. Static fluids, right? What we did at the beginning, and fluids in motion. All right, there's like 2 or 3 problems on this in the assignment and assignment chapter 9. So make sure you review those. Okay. So I want to give you guys a 10-minute break, and then we are gonna start with solids and gases. Chapter 10, talking about temperature and a little bit about the kinetic theory of gases. All right. So we're gonna introduce that today, and then tomorrow I'll be doing, maybe even today I can do some problems, but tomorrow I'm gonna be doing quite a few